Oh, every time I have to apply this background. Okay, so tutorial 7, and then I'm guessing, or I'm hoping that you have already tried it. It's quite simple actually. I mean, it's much more simpler than the rest of the tutorials. Some of them, for me, I think it was. I mean, this is much more easier comparatively, other than others. But the thing is, we need to understand the process or what is happening, why the answer for one is okay, for another one is not okay. It is not about just finding the knowing the answer, but the reason why it is the answer like that. Okay, so, and another thing I wanted to say, for this tutorial, thermochemistry and kinetics, yeah, in your lab report as well, experiment, the much of it will be in the discussion. Okay, much of it will be in the discussion, not in the methodology or calculation. There is not much calculation, but in the discussion as well. I mean, there should be much about the endothermic, exothermic, the process, why happening, where the heat is going, how the heat is dissipating, why it is happening, how it is happening, all those things. Okay, so question number 1, for an endothermic reaction, what actually happens for an endothermic? So endothermic means it is taking the heat. Exo means exiting. I remember in that way that exo means exiting, but the heat. But here endo means it is taking up the heat from the environment. So it will be absorbing, the heat will be absorbed from the surroundings, which is called system. In the system, the surroundings, it has the environment around it. And the enthalpy changes is negative. No, it is not. The del H is positive. Del H is positive for endothermic, right? So that is how we know that we have to provide heat to the system or from the surroundings. We have to provide the heat. Will go to the to the system. Let's say it's a system. It's a reaction is going on in the system. So B is the answer. And then the C, it says that the enthalpy of the reactant is higher than the enthalpy of the product. It is indicating the energy diagram. The enthalpy of the product is, the enthalpy of the reactant is higher than the enthalpy of the product. So this is the reactant. This is the product. So if reactant enthalpy is higher than product, that means it is releasing heat. We started at this point where the del H is here. Sorry, this is not del H, H only. So this is the heat. We started from here and then we reached here. So the del H is actually releasing the heat to come to this point, right? So this is not the answer, because this is for exothermic reaction. Both A and C are correct, of course not. Question number B, it says the activation energy of a particular reaction depends on the temperature at which the reaction occurs. That means the activation energy is this part, right? This is the activation energy. EA is denoted by EA, the activation energy. Yeah. So the activation energy, it says that of a particular reaction, let's say A and B are reacting together. This is a this is the energy diagram for that reaction, and the activation energy is until this point where X, this point until X, it has to go, and then only it will move towards forming product. So this activation energy is depending on what? The question is saying that it depends Does it depend on the amount of the reactant we put? Does it depend on the energy or the heat we put, or does it depend on the what do you call it, type, the purity of the component? It doesn't. It is an intrinsic property. When A and B will react, wherever they react, whatever amount they react, where you do it in the lab in 50th floor or in the ground floor, same. This is the intrinsic property. That is, they will have to, by themselves, for themselves, they have to cross that. This is their own barrier. They have to cross over to go to that product side. So it does not depend on the temperature at which the reaction is occurring. Temperature can help it to cross the barrier faster, easier, or harder, right? It has always positive value. Does it mean that it will always be negative? No. It has always positive value means it cannot go this way, right? If it is, then it will be negative value. So can it go to that? Can it follow this path? No, it cannot follow the negative. It cannot have a negative energy. The negative energy means, a negative activation energy means what? That even you bring it together, before even you bring it, that the reaction is occurring. That means without any heat or any influence, the reaction is occurring by itself, and then the product is forming, which is not, it cannot happen that way. That is a basic rule of chemistry and physics that we will not discuss much. But EA is always positive value. It cannot have a negative value. You can think about it that then if it is a negative value, what will happen? Okay, what can happen? You probably will have some crazy ideas, but that will be nice. It's okay to have some crazy ideas sometimes. All right, so option C says it is is unique for that reaction and can never be changed. It is unique. Half of this is true, right? Half of this is true. This is unique for that reaction. It is always same for that type of reaction, but it cannot be changed. This is not true, because if I use catalyst, I will have different pathway, different activation energy. The catalyst will reduce this activation energy for that. Activation energy is the energy absorbed or released in a chemical reaction. No, it's not true. It is the enthalpy, right? What is absorbed or released is a form of heat, is the enthalpy for that reaction. Question number 3, I'm going fast, but if you have any question, please stop me anytime and then you can ask the question, okay? Question number 3 says the relative energy change of the reactants and products in a chemical reaction is represented on the following diagram: reactant and product. The numerical values of the enthalpy change del H and the activation energy EA for the forward reaction are, so it is quite easy actually. I think you already have done it. We just have to 200 minus 150, so it's plus 50. Activation is plus 50, or there are two plus 50, yeah. And del H of the activation enthalpy, the change of enthalpy is 150 minus 50 is negative 100 plus 50. So D is the correct answer for this. Question number 4. It says use the following diagram to answer the question. Progress of the reaction, that means the reaction is going this way. All right. So I'm going to ask a question now. I hope that you will participate to try. If the reaction is going this way, right, how do you find the rate of the reaction? How will it be? how can you find the rate of the reaction? Okay. Where is your shared window? Sharing is paused until you return to the shared window. I am in the shared window. Oh, okay. Yeah. So how do you find the rate of the reaction from this type of diagram? How do you find, and what does actually rate of the reaction tell you? Okay, there is some answer. Sir, can you repeat question 3? Question 3, okay. The relative energy change of the reactants and products in a chemical reaction is represented on the following diagram. So the reactant, we started here. The reactant has an enthalpy or heat of the reaction. Enthalpy is the heat of the reaction, right? Or at the beginning, they had 150, the heat, let's say that, kilojoule. Okay, we express it in kilojoule per mole. Kilojoule per mole, let's say, or it can be any other. Just for example, I put kilojoule per mole. Okay, and then the reaction is going this way. We started A plus B, we mix. A plus B, we mix, and then this is the reaction path. So 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, 6 minutes, 7 minutes, 8 minutes, 9 minutes, 10 minutes, 11 minutes is continue. So 1, 2, 3 minutes is nothing change. But at third minute, when it started to go up, the heat of the reaction started to go up, and then it reaches to 200 kilojoule per mole. And then suddenly, not suddenly, I mean, it started to decrease. It's decrease, and go all the way at 3, 4, 5, 6. Sixth minute, it goes to like 50 kilojoule per mole here, right? So this is the energy diagram. We know that this is the barrier or the mountain the reactants have to overcome themselves. It is among, this barrier is among themselves. They have to overcome this one. Only then the reaction will be occurring. Until here, at this point, until this point, it is, the reaction is not occurring. It is, they are fighting, but new bond is not formed yet. All right. Only when they cross this barrier, the new bond started, A and B started to form a bond. At this point, still they are A and B. A and B. All right. So they are fighting together, colliding each other, but only after they cross over that point, A, B started to form a bond. Somehow, I mean, just for example. So this, so now the barrier they have to overcome is the activation energy. It is activation energy, right? So how much is the activation energy? It reaches until 200. So 200 minus, we started 150. So 200 minus 150 is 50, right? So the activation energy is 50, and it is of course always positive. It's always positive, but from here to the final energy or enthalpy is this one. So 150 minus 50. 150 minus 50 is the, so this is 100. So this is the enthalpy of the product. That means the enthalpy of the reaction, actually, the reaction's enthalpy, it changes. It started from 150 but reaches into 50. So the enthalpy change is 100. And it is negative 100 because the final is 50, right? The final is, so I should write in this way. So the final is 50 and it is coming from 150. So total is, I mean, the final is negative 150. Sorry, what I'm doing, 100, negative 100, yeah. So it is negative 100, the enthalpy change, and the activation energy, which one is this? Activation energy is positive 50. Hope that answer your question. Okay, and my question was for this. Progress of the reaction, right? How do we measure the progress of the reaction? Can anybody help me out? How do we find the progress of the reaction? All right, let me make it a bit simple. How do you find the progress of your studies? Let's say that you are preparing for your mid-sem test or for your presentation next week. What is the progress? How do you measure the progress? Can anybody tell me? Upathi. Upathi not there. Noor. Why? Hey, hello, you can hear me or not? Okay, Noor is there. Not sure. Vanessa, no one.
Sorry, so can you repeat your question because just now I went down for a bit.
Oh, okay. That's why so quiet. Everybody went down or what? So my question is that this is the progress of the reaction, right? So actually, what do we understand by this progress of the reaction? Actually, what is happening? How do we measure, or how can I quantify the progress of the reaction? And the analogy I was giving is that next week is your presentation for the project. How do you measure the progress of your preparation or progress towards the presentation?
Make sure everything is ready already and research is all done.
Oh, that's good. That's good. So the progress of the reaction is that I have to quantify, right? When you're putting on the graph, first of all, when you're putting on the graph, you have to have some quantity or some values on the graph. You must have some values. If you say, okay, it is very good, it is very nice, it is less good, it is very bad, you cannot put in that way in the graph. You cannot draw any graph. You have to have some values, okay, for progress. So to know the value of the progress, how do we measure the, okay, for example, of the preparation for mid-sem test or for the presentation, okay, I wanted to have 10%, 10% of is done, 20% of is done, 30% of done, or 1 pages I have written, 2 pages I have written, 3 pages I have written, like that. We have to quantify. Same goes for the reaction, progress of the reaction. Reaction occur in first minute or 10% reaction occur. 20% of the reaction occur, right? Or how much the rate of the reaction is going on, the rate is very high. That means 20 per time. At minute 1, it is 20 per minute, right? 20 per second, 20 per minute, something. And then here it is 80 per second. Suddenly it becomes 80 per second, right? So this is how the progress of the reaction goes, and after that it will be stagnant. It will not proceed anymore. 85, 85, 85, 80, all 85, 80. That means we understand that, okay, the reaction stopped. It's not going or doing anything. So this is how we know the progress of the reaction. This is just to, I wanted to do it to relate it for yesterday's lab. Okay, So now it says they use the following diagram to answer the question. Process of the reaction, which of the following are the values for activation energy? Activation energy, once again, I'm not going to detail. Where we started from here at 150. So this is the reactant, let's say A plus B. They are reacting A plus B, right? Has to be like this, and then it reaches the hill is top up there. So this is the activation energy, and it is always positive. So you cannot draw activation energy in this way. You cannot draw in this way. Again, once again, if you draw in this way, and you can try to interpret what does it mean, you will find interesting thing. So this is activation energy. And 250 minus 150, that means activation energy is 100. All right. And it is the endothermic reaction because the product enthalpy is higher than the reactant enthalpy. So it is 200 minus 150. So plus 50 it is. So know that it is the correct answer. Now, every time in the exam, it will not be given to you that, okay, this is the diagram, find out what is the EA and enthalpy. Sometimes it will be just given you open question that this is the enthalpy of the reactant and this is the final enthalpy of the product. Find out the reactant or path. So it is arbitrary. It's up to you how much you want to produce and how big you want to make the graph. You can make smaller or bigger. It's up to, I mean, the scale is up to you, but sometimes student is given, the student do like this. Okay, it is not accepted. Don't be so stingy in using your paper. There are a few marks on it. Okay, so make sure that it is nice and understandable. So we can read, we can understand. All right. So in this type, I usually do not give marks. Question number 5, once again, the same thing, but this is what is X, what is Z, what is Y. It says that the reaction can occur between methyl chloride molecule and a hydroxide ion is what is true for them. So methyl chloride is reacting with hydroxide. My question now, it is B. Bilal, what is your, what do you say, B? Is it? You're saying? Okay. Oh, sorry. So this is not 250. Yeah, it's 300. Yeah. Sorry. It's 300. So 300 minus 150. Yes. So it is 150. It's not 100. Sorry, my mistake. I thought it's 200. I thought in that way. So it is not true. So it should be, answer should be B. Yeah, not C. B. Thank you for the answer. Yeah. I was asking. So is it correct or not? Now. Okay. So question number 5, it says that the following reaction can occur to completion in aqueous solution. Methyl chloride and hydroxide ion is reacting. So this methyl hydroxide and chloride ion reforming. My question was where this hydroxide ion is coming from. Can anybody answer? The hydroxide ion is coming from where?
The liquid.
Yeah, liquid, but what type of liquid?
Alkaline solution.
Exactly. So this is hydroxide. When you write in this way, I think that you have not taken care of the redox reaction. Yeah, so you should try to study redox reaction. This hydroxide ion is coming, or acid base, sorry, acid base of those. It is coming from sodium hydroxide or potassium hydroxide, lithium hydroxide, potassium hydroxide. These are the alkali, right? This is strong alkali. So this is base also, you can say. So this is sodium and hydroxide is negative, potassium plus. So this is the hydroxide is coming from the base or alkali. Reaction, the energy change during this process is illustrated by the following diagram. A reaction can occur between methyl chloride solution molecule and hydroxide ion. When will the reaction occur? Every time they collide, will there be a reaction? If not, I mean, you already know the answer, it is not the true, but why? Can I ask anyone why when they are colliding, why there is no reaction? Consider this the main question. Munib, I don't care if you guys hate me for name calling, but still I like to do that. So students, at least, oh, my name is calling. He's calling my name. At least you'll be paying attention to. So Munib, you there or not?
Yes, I'm here.
Yes. So why A is not the correct answer? When there is two are fighting, why there is no reaction occurring? Anybody wants to try?
Because particles already collide even when they are in room temperature. They only react when they make certain they have enough energy.
Eric, I couldn't, I mean, quite catch it. So can you once again repeat it?
I said like when it's in a solution, particles already collide together, but
Yeah.
they need enough energy to react, to have a reaction.
Yeah. So where this energy comes from then to do the reaction?
From the surrounding, from heating or giving it a catalyst or something. Depends.
Exactly. Yeah. So I understand your question, but answer. The simplest way is they have not have the enough activation energy. Okay, to cross the activation energy, they should have crossed this energy. Once again, I'm not going to go into detail because I already. So they should go cross over this mountain, the hill, the activation energy hill. They should go up. Maybe they are fighting here. They are fighting. They are fighting. They are fighting. They are fighting. Only then, when they reach here actually, they start to form the bonding. That means methyl, this methyl molecule and this hydroxyl, they will form and chloride is kicked out. So this is happening at this point. Before that, still methyl chloride and hydroxide, methyl chloride and hydroxide everywhere. So this is chemistry you can actually relate to our everyday life as well. Some people always complain that I try, I could not do it. I try many times. The problem is we try, but we maybe a little bit more trying will get us to that activation energy curve. Okay, and then the reaction will occur. So we try, but a little bit more need to try so that we can cross over that activation energy. So students, those, we have to study a bit more to go over that curve so that we can cut a good figure, right? So this is it. Now question number 6. A methylated spirit can be used as a fuel in camping stoves as shown in the following equation. This is, what is the symbol of this? Does anybody know what is this? This one? CH3CH2OH. We call this is oxygen, isn't it? This is oxygen, we know. But what is this? Does anybody know?
Ethanol.
Yeah, ethanol. So this is, where is it? Oh, so this is the same ethanol. It is in the, can be used. Methylated spirit is actually not ethanol. Methylated spirit is poisonous, it's toxic. It is ethanol, but there is a mix of methanol, CH3OH. CH3OH. So sometimes you will notice that people die because this ethanol is a hard drink. This is alcoholic drink. This ethanol is an alcoholic. Even though it's alcoholic drink, it cannot be more than 50 or I think 48%, because if more than 48%, it is very bad for health. Only the maximum is for even 1% ethanol is also bad. Now a new research came out. But anyway, people sometimes they drink this ethanol and they die of the toxic effect, because that is not ethanol. There is some methanol, CH3OH, is mixed to prevent it from drinking. Otherwise, people will just drink it and become drunk, and so to just prevent that one, the methanol is added to this ethanol, and that is called the methylated spirit. So it is not a drinkable. It is very bad. It is flammable, but it is methanol will kill people. Ethanol does not kill immediately, but in the long run, as any do. So where am I? Methylated spirit, when it is reacting in presence of oxygen in the air, how does it react in the oxygen? Does it mean that if we just keep the ethanol and the air got oxygen, right? We are breathing, air got oxygen, so it will just burn? No, it will not. It will evaporate, but it will not burn. What do you have to do? You have to give a spark, like a match strike or a lighter. You have to, what do you call it? Lighter, start the fire, spark, so that it will go there. So I forgot which of the following best explains why a lighted match is required. Okay, so why do we need to use the lighter or a match? We have to strike a match. Why it does not just start fire? Or in our kitchen, the LPG, right? Oh, we are talking in the lecture. So it gives the activation energy. Just maybe 1 or 2 molecules gives the activation energy enough, and then they cross. When they start to form the product, then they release the energy. So other molecule get that energy, and then the fire. So that is how the fire starts. So if you see the gas burner, you will see that one side started to fire, and then like other way all around it is getting, not at the same time, like it's getting the fire all around one by one. So this is maybe in a broad sense we can relate in that way. So the match is giving the energy for only few molecules, maybe 1 or 2 molecules, to get the crossover, that activation energy, and give us the light. One thing is there any question? Okay. What was that? Oh, okay. I wanted to say that this, let's say, is methanol, ethanol, or spirit, or LP, NG, liquid gas, methane gas that is in our at our kitchen, or this type of thing, or a candle is burning, right? The candle is burning. Let's say talk about the candle burning, and this is a candle, and this is the flame, right? This is the flame. So in this flame, you will see this is blue color, B. This is yellow color, and then this is here is black color like that. It's like black. So okay, BLA, black. It is blue. This yellow. Why there are three different colors for one flame? One thing I want to say, I just want to, we have enough time, right? Okay, we have enough time to discuss this different time. And then how do we get the heat actually? We do not, once again, just for relating this thing, I am going to draw the activation energy curve like this. So this is exothermic reaction. This is a reactant. This is product. So this is exothermic reaction happening because it is the product is less than reactant. So can you, do you understand what is happening when this is a fire and we are getting the heat out of the fire? Until this point, let me take a different color. It is interesting if you understand, and I hope that you will get a quite good insight. So until this point, the reactants, the gas, let's say the gas, we are burning the gas or candle, and until this point, you are not getting the heat until this point, until the middle of this curve. You have to provide heat, right? You are not getting heat. It is taking up heat only from this point until this point, we are getting the heat out of it. And this heat is helping us to cook our food. Only this much of heat. And that much of heat, it looks in the diagram that I draw, it is not on the scale, it is not perfect. Maybe I should draw a big like this, so it would be nice. But anyway, just to show you. So this amount we are getting the heat from, and this heat is helping us to cook our food or boil our water. Now, this heat is being released, not, oh, okay, before that, the gas and these molecules, they are together, right? They are here and they are fighting. They are colliding each other, they are fighting, but their fighting is supposed that we will get more heat because they are fighting. So, you know, when people start to fight, the environment is very hot. We're supposed to feel that heat. But when they are fighting, we are not getting any heat out of it. But when they are forming the bond, the heat is releasing at that time, right? The heat is releasing that time when they are forming the bond. So this is interesting thing. When they are colliding each other and supposed to have more heat, we are not getting heat. We have to provide more heat. But when they are forming bond, become quiet, then we are getting the heat out of it. Here it is this side. It is more, bluish color because this side. Because this side, the molecule that is burning, and then let's say that we know that when a particle they absorb heat, they become excited and the electron go to the next level, and when the electron comes back, they release the energy in a form of heat. You remember from our spectroscopy, right? We studied that spectroscopy. So here the molecule is, getting the heat, and then they are becoming more excited and going to the next level, coming back. So they are giving blue light. At this position, there is only carbon. Here is other for the candle. Here it is the the wax is actually hydrocarbon. I'm not sure whether you know about hydrocarbon. Okay, so we'll actually learn from week 10 onwards about the hydrocarbon and organic chemistry. So hydrocarbon means which is CH like that. So hydrocarbon are there, so they are absorbing light, excited. The electron is coming back. They are, releasing blue light. So that level they are excited. But here it is orange color of light or yellowish light. That means here is only carbon. After they become burnt at this position, they become burnt at this position, then the yellow color. Okay, this is the golden or yellow color, right? So here carbon is left over. Carbon atoms, they are absorbing light, and when they are releasing the light, the energy, carbon atoms release the frequency of the light, which is yellow color. And then the black is the soot or the charcoal that is left. So this is just to inform you so that you, if anybody asks you, why do we see different color and what is actually happening when we start the gas stove, so probably you can answer them. Question number 7. Any question? Anybody? All right. Question number 7 says that which changes increase the rate of chemical reaction? Yesterday we have already seen it, so I don't need to express more. Increase the concentration, yes. Of an aqueous solution, yes. Increase the particle size of the same mass of solid reactant. Does it make any help? Particle size. It will reduce the reaction because particle size is smaller means bigger surface area. Bigger particle size means smaller surface area. So it will not help. Only 3, yes. 3 will increase the temperature. To some extent, it will help. So 1 and 3. Question number 8. Any question? Anybody has? No. Question number 8. Which of the following factors will increase the frequency of a collision between reactant particles in a chemical reaction between two gases that are sealed in a container? So which of them of the following two will help to increase to go to the product side, right? To the product side, right? Increase the pressure of the gases. If we increase the pressure of the gas, what will happen? The collision, yes. Pressure of the gas means this is a container. This is the container. How do we increase the pressure? Have you ever seen a bicycle pump? Right, the bicycle pump is the pumper here, and then this is a pumper, so we can lift up and press it down. So when you press it down, right, from here to here, the volume decreases. The volume decreases. Volume decrease means the concentration increases and the pressure of the gas increases. So when the pressure of the gas increases, that means the particles are more nearby. So they have no choice but to bump to each other. When they are big space, they probably will bump or probably will not. But when they are less space, they have no choice. They have to bump each other. So it will increase the it will increase the pressure of the gases and in a sealed container. Introducing an inert gas to the container, yes, that helps sometimes, but there are some, what do you call it? There are some exception in that. We will not discuss more. Maybe we will discuss it in degree when you go to the degree. Okay, so another thing is the increase. Where is that? Increase the volume of the container. If we increase the volume of the container, that means depressurize. So if we depressurize, it will have less collision in between them. Question number 9, it says the reaction of heated magnesium with steam is faster than the reaction of magnesium with cold water. This is mainly because why it is faster, right? Why is it faster? The coating of oxide on magnesium decomposes when it is heated. Doesn't matter because they in the magnesium. Okay, the question is the reaction of heated magnesium with steam is faster than the reaction of magnesium with cold water. Oh, so no, the magnesium oxide, it will be formed when it is more hot water or hot environment is hot. So magnesium oxide will be formed on the surface of magnesium. So let's say this is the magnesium. Magnesium is a metal, right? So like sodium, magnesium is also a metal, and it is used in the alloy in steel alloy to make it to iron alloy to make it steel. Okay, and also okay, since we are here, just to inform you that magnesium is used in that type of composite we call when in the metal there are many things mixed together, we call it composite. Not in the metal, in the plastic, in the other material as well. When many things mixed together, it's called composite. So the magnesium is used in the metal, like your car tank, right? The petrol tank of your car. It is made of magnesium alloy. Most of magnesium in that alloy is given because magnesium, when there's alloy, it reduces the possibility of sparking. Magnesium reduces the possibility of sparking in the container. Otherwise, if no magnesium, what will happen is you put in the metal container or just a steel container. When the car is moving or pumping, the fuel will be turbulent, right? Very much, and then probably maybe there is a possibility that there is a spark. But if it's a magnesium container, there is not. But still, there are some cases, right, that got fire somehow. I don't know. It is from the petrol tank or from somewhere else. Okay, so question A, answer A is not correct because coating of magnesium will be formed when it is heated, actually, not reduced. Option B says in cold water, the water molecule do not collide as frequently with magnesium. It's not true as well because water is in liquid form. And yeah, this is true, but cold water means they are stable and also they do not collide that frequently. But the best answer is option C, that the fraction of particles with energy greater than the activation energy is higher in the reaction with steam. So it's all about the activation energy. All right. The activation energy is higher in the steam because steam is hot air or hot water. Steam is hot water, so it already has the heat in it to overcome the energy barrier. Option D says the reaction with steam goes by an alternative route. That no, it doesn't. The only alternative route is happen when there is a what do you call it? A catalyst. When there is a catalyst, only then it happens. Okay, so question number 10 says consider the reaction in which hydrogen peroxide decomposes in the presence of some chopped liver, which can chopped liver, by the way, chicken chopped liver, yeah, which can catalyze this reaction. Hydrogen peroxide, it always decomposes, actually, it always decomposes and gives us oxygen, and that is why it is a very strong disinfectant and also also a strong, you know, what do you call it? Bleaching. It has a very bleaching, high bleaching capability, hydrogen peroxide. So in one experiment, this reaction was monitored by two sets of students, group 1 and group 2. They measured the mass of oxygen gas that evolved at regular intervals over time. There was just one difference between the reaction condition they used. The graph they obtained are shown below. So now they are quantifying, since they are doing the graph, the data, they are quantifying the how much of oxygen gas is coming out, because it will produce oxygen, right? It will produce oxygen. I mean, if we put hydrogen peroxide in presence of this chopped liver, the oxygen will come out. So this oxygen is coming out, how much oxygen coming out per time, per minute, 1 minute, 2 minutes, 3 minutes, 4 minutes. Group 1 and group 2. Group 1, it says that they reach to this maximum number of oxygen. Okay, let's say this is X amount of oxygen, X gram of oxygen, X gram of oxygen. I don't know, it is not quantified here, but X gram of oxygen. And then group 2, they also reach to this X gram of oxygen, but it is at the 3.7, I think, 3.75 or something like that, 3.75 minute. Same oxygen, and then after that it did not increase or decrease, it stays stable. Of course, after some time it will decrease, but until 7 minutes it did not decrease anything. So what is the key? What is the difference between two groups? What group A1 did that group 2 didn't do? Or what was the facilities that group 1 had? Group 1, it used a higher concentration of hydrogen peroxide, right? And group 2 that says that, okay, option A says that group 1 added greater amount of hydrogen peroxide to the flask. But the thing is, the more is the liquid form, doesn't matter you add 20 milliliter, 30 milliliter, 1 liter, still the reaction is going that way. That reaction is going to the same path. It is following the same path. Option B says the group 2 chopped their pieces of liquor into smaller pieces. So yeah, smaller pieces. The different result obtained by the two groups could be explained if the difference in the reaction condition they used was that. Oh, so reaction conditions, everyone is the same thing, but what is the different reaction conditions they use? It is the chopped liver. It is not a condition of the reaction, because chopped liver is working as a catalyst, and catalyst is not part of the reaction. It does not take part in the reaction, right? We already know the definition of catalyst, that it does not take part in the reaction. At the beginning and at the end, it is still the same. If it is magnesium, it's still magnesium. It is chopped liver, it's still chopped liver. But it will just facilitate the reaction, so it does not take part. So it cannot be the part of the reaction. And that's why A is not correct, because everybody is doing using the same amount of hydrogen peroxide, only the concentration is different. So group 1 is using the higher concentration, group 2 is using the lower concentration. And since they are using the same type of reaction condition, different reaction conditions, that means the flask of hot water, group 2 set a flask of hot water. It doesn't, we do not see whether this is an exothermic or endothermic reaction that needs a hot water or not. So we cannot say for certain that we cannot say that whether it will take the hot water from there. Question number 11, it says that zinc metal reacts with 0.1 molar hydrochloric acid to form hydrogen gas. Okay. Zinc metal reacts with 0.1 molar hydrochloric acid to form hydrogen gas and zinc chloride solution. The production of hydrogen gas is more vigorous if zinc is powdered rather than the large pieces, because of the collision between zinc and particles will be higher. Because of this, frequency of the collision will be higher because the surface area is higher, bigger. So C will be the correct answer for this. Question number 12 says the increasing the temperature of a reaction increases the rate of reaction. Which of the following does not increase when the temperature is increased? If even the temperature is increased, why some of them will not be increased, right? The average speed of the particles. Okay. Okay. Oh, that's why you should read it carefully. Yeah, I was thinking, why is the average speed of the particle will not, but it doesn't. It says that not. Wait, the following does not increase. The average speed of the particle will increase. Yes, this is correct. Number of particles with sufficient energy to react. Yes, it will increase. The more particle will go to reactant side, because we already have seen the Maxwell-Boltzmann, the figure that more particle has the sufficient energy to react. But the activation energy does not increase. Even though doesn't matter how much temperature you increase or decrease, the activation energy is always same, right? And by adding a catalyst, you can find an alternative path to bypass that activation energy, but activation energy is still the same. The frequency of the collision will also increase. So all three, A, B, and D, are correct. That's why it's not the correct answer. It does not increase. Question number 13 says, which of the following statements about why reaction rates are faster at high temperature is incorrect? Okay, once again, which is incorrect is the mean speed of the particle increases, hence the collision rate increases. This is correct, because if high speed, of course, they will more frequently go here and there and collide each other. The colliding particles have more kinetic energy on average. Yes, that's true as well. So this is not the answer. Question option C says the activation energy is low. So a high percentage of collision are successful. This is not correct. Activation energy cannot be lower or higher, so it doesn't matter. So C is the incorrect, so it is the correct answer for this purpose. Question number 14. The diagram below shows the Maxwell-Boltzmann distribution of molecular energies for a gaseous system at two temperatures. The rate of a chemical reaction increases with temperature mainly. Rate of chemical reaction increases with temperature mainly. Why the chemical reaction increases with temperature? Because the activation energy increases. It cannot increase, it cannot decrease. So A and B both are incorrect. The more collision occur when with energy greater than the activation energy. Yes. So because here, if we not here, let's say anywhere, let's say here, right? Half of both of these curve you can take. So we see that, sorry, this is not correct. So this is energy 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So out of this 10, take any position. Let's say we take 4 position, right? So in this case, more particles under this 310K curve, because the curve is fatter in that sense, or is fat in that sense. But 300K is less. It is not that fat, so it will have less particles under it. And that is why it is the correct answer. Question number 15. Which of the following happens when a catalyst is used in a reaction? Which of the following happens when the catalyst is used in the reaction? The activation energy of the reaction decreases. The activation energy of the reaction increases. The number of collision between particles decreases. The proportion of particles with high kinetic energy increases. Which one? Activation energy cannot increase or decrease, so both of them are technically, factually incorrect. But again, there is no better answer than this, so A will be correct in that way. All right, but actually they are providing alternative path to overcome this high activation energy. All right, so all this 15 testing question has been completed. Any question from you guys so far? No. If no, then we'll move to this thermochemical, the past exam questions, structured question. But before that, give me some time. I bring some tea. Wait. Okay, so come back. 5 minutes, yeah. Okay, I'm back here. So question, past exam question, we will be doing it quite fast. Actually, it's not much for past exam question and quite easy. Actually, it is easy. That powder ammonium chloride powder form has been used in industry to adjust the chloride concentration in ammoniacal etching bath, and it dissolves in the etching bath to form aqueous ammonium and chloride aqueous solution. And the thermochemical equation for this is it goes in this way. So it is an endothermic reaction that needs 16 kilojoule of heat. So it's not that very, it doesn't need that much of energy, but still it is an endothermic. So this is a metal processing thing. So it is an etching bath. So metal need to be etching sometime the surface for cleaning and purpose and for other things, fabrication process. So this 16 so now it shows that since ammonium chloride, it is taking the heat from the environment, right, from the surrounding. So if we touch that bath, we will feel it cold because it is taking the heat out of the environment, out of the surrounding. And that is why sometimes, I was telling that sodium chloride, if you dissolve sodium chloride in the water, you will feel it's a little bit cold, right? Because it takes the heat to become dissolved in the solution. What is the effect of the bath temperature? So bath temperature, the bath will be cold. It will become cold, or it will feel cold. Suppose the activation energy of the reaction is 56 kilojoule per mole, right? It's 56 kilojoule per mole activation energy, and now we have to provide, or we have to, you have to draw a design. So it started from here. It is already given at 40. It is given. So 56. It will go up to this 56 to here 56. Activation energy EA will be 56, right? So it is going up this part, and then it is an endothermic reaction. So so it will be from here 40 to 56. So in between this term, it is 50 plus 16. And this is, of course, always plus. It is 46 kilojoule per mole. All right, 16. It was determined that an etching bath, which is not working properly, has a chloride concentration of 160 gram per liter. An etching bath that is working properly must have chloride concentration of in the range of 165 to 195. Gram per liter. The etching bath has a volume of 800 liter. Calculate the minimum amount of powder ammonium chloride in kg to be added to the bath so that it will be working properly. So the etching bath is not working properly because it has only 160 gram of chloride. Remember, it is saying is chloride. The problem is given in chloride, but the condition, it is given in ammonium chloride, right? The condition says that minimum amount of ammonium chloride powder I need. But when it gives me the problem, it is saying that it is in chloride form. So we have 160 gram per liter in the system, but to work properly, at least 165 to 195. Between this range, it can be 170, it can be 171, it can be 179, it can be 820, 182. So all this range, between this range, it must be. If it is 196, probably it will not work. If it is 164, probably it will not work. So it must be within this range. I already have 160. So to go to the, of course, I'm not giving you the maximum, the minimum I will need to work, because why should I give more when I can get it done by providing 165, right? So, so 165 minus 160, that means 5 gram, the minimum. I just need the minimum one, is 5 gram per liter. I need, right? And it is 800 liter. So if I need extra 5 gram for 800 liter, I need 4,000 gram. I need 4,000 gram of chloride ion. Remember this thing, right? It's a chloride ion I need. But the problem says that minimum amount of powder ammonium chloride I require. It does not say that minimum amount of chloride. It says ammonium chloride. Now we know that this is ammonium chloride. Where is it? Ammonium. Yeah, this is the ammonium chloride, right? This is the ammonium chloride. So ammonium chloride. Ammonium chloride. In ammonium chloride, how much chlorine is there? So, okay, to make it easier, how much ammonium chloride should I use to get 4,000 gram of chloride? Right, 4,000 gram of chloride. How much chloride, ammonium chloride, should I be using to get that much of chloride? So now we see that chloride in ammonium chloride, that is ammonium chloride is the molecular weight is 50, let me check, 53.4, 53.4, just rounding off, 53.4 gram of ammonium chloride molecular mass, but chlorine is 35.5 gram per mole, right? So if in 1 mole, there will be 53.4 gram of ammonium chloride, out of which is 35.5 gram of chloride. All right. So 4,000 gram of chloride I need. And then it will be let me write again, 3.4 gram of ammonium chloride. Okay, over 35.5 gram of chloride. So chloride cancelled out, and from there I see that I will need how many grams? 6,036 gram, I think. Yeah, 6,036 grams, something like that. You can do the calculation, and then in kg, since it says that should be in kg, so we have to divide by 1,000 gram per kg, and then we get 6.04 kg. Just round off to 2 significant figure, 6.04 kg I need. All right. So the thermochemical equation provided above, calculate the energy in kilojoule required to decompose 500 decimeter cube of ammonia and at 101 kilopascal and 200 degrees centigrade. So we have to draw, and then it is positive, so it will go up, it will not go down, and then this is how. Using the thermochemical equation provided above, calculate the energy in kilojoule required to decompose 500 decimeter cube. Decimeter cube is equal to liter, yeah, of ammonia at 101 kilopascal and 200 degrees centigrade. So at this temperature and pressure, 500 liter means how many moles? PV equals nRT. Again, we have nRT. So from N, we can find, if we put this value, this is the V, this is the V, this is P, and this is T, right? Of course in Kelvin, so you have to add 373.15 Kelvin. So altogether it will become Kelvin, right? I have to convert it to Kelvin again. And then R is the constant. And from there we'll find the number of moles, N, how many number of moles, and then we just multiply with 92. But only one condition, that 2 moles, this 92 kilojoule per mole is, but it is 2, right? So over 2 moles will need 92 moles of energy. So how many moles? N is how many moles will be produced and how much energy will be required to break it down. This is again the same thing. I'm not going to draw. You have to draw in this way, and then if we add catalyst, it will go in this way because this activation energy is here and activation energy is there. It is reducing or alternative path, actually, not reducing, alternative path. So it bypassing that higher energy. Okay, so question number 3, it is almost the same thing. It's actually same thing. I'm not going to discuss. You have to do it. Only the thing is here, it says that state the oxidation number of nitrogen in nitric oxide and nitrate ion. So nitric oxide, what is the oxidation state in nitric oxide? Nitric oxide, we see that let's say that it is 0, unknown X, and oxygen is always -2, so positive X, right? So it should be 0. There is no charge carried to 0, so X and nitrogen will be positive X. Nitrate ion is positive X, and oxygen is -6, equal to -1. Right, so it will be X will be sorry, not X, it's given here already, so I just need to put the value +5. Complete the following half reaction for the conservation of acidic condition. And for the acidic condition, that means I do not need to bother about hydrogen, where the hydrogen is coming from, right? In that way. So nitrate ion, and then it is forming the nitric oxide. One oxygen atom is, two oxygen atoms is left over. So 2 oxygen atom can produce 2 water molecule. If it produces 2 water molecule, then I have to add 4 hydrogen ion here. 4 hydrogen ion. This is coming from the acidic condition, but now it's good. So 4 hydrogen here, 1 nitrogen, and 2, 3 oxygen. So all balanced. Only the electron or charges I need to balance. Now it is here 1 negative and here 4, because this is 4, right? So four positive charge. So the balance is 3 positive charge. 1 minus 4 is 3 positive charge. So I have to add 3 negative charge here. So 3 electrons, sorry, so that I will have it balanced. And that is how we balance it. Now it is balanced already. It says that write another half of the reaction. Another half of the reaction is the silver. I think it is given here, right? Silver metal. So the silver metal will be produced, and then silver is reacting, but silver is metal. So it is easy for silver to give up electron. That electron actually coming from there. So 1 electron. Now, since I have to have 3 electrons, I can just find this way, right? So 3 silver atom is producing 3 electrons, and these 3 electrons are being used here. Okay, so the full is you just need to sum these two up, this and this, and then you get the reaction. All right, so this is it actually, basically, and then forward reaction is all the same thing. Do you have any questions so far? Anyone? Listening? No question. Okay, good that you understand. And there will be an announcement today on Canvas. I stop recording first.